Hello, this is the second lecture that deals with multiple alternatives. In this lecture, we'll present a method for defining combinations of independent and mutually exclusive alternatives. We'll also demonstrate the selection process for more involved situations using two criteria, the rate of return criterion and the benefit-cost ratio. Let's look at our procedure for combination alternatives. It's basically a brute force method. We'll construct the logical combinations of the alternatives that are technically feasible and then eliminate any that exceed a budget constraint if we have such a constraint. Let's look at our example. We have a manufacturing company that is seeking to expand its market in some new areas. So we'll call these areas E, F, and G. And there are a number of potential distributors available for serving these areas. So here are the distributors listed by area. And we've identified the distributors with the letters V, W, and X for area E, X, Y, and Z for F, V, W, and Z for area G. Of course, the X for area F is the same as the X for area E. The W is the same, and so forth. So here's the situation. We've got three areas and a number of potential distributors. The company wants to figure out what's the best way to negotiate with each of these distributors to maximize its sales revenue. So here are some simple combinations. For area E, of course, we can do nothing, stay out of that market. Or we can try to negotiate a deal with distributor V or W or X. And these are the investments required for those negotiations. If we look at area F, we again have four simple combinations: do nothing, distributor X, Y, and Z. And the investments are listed here. And last, we have area G with, again, the four simple combinations and the respective investments. Now, there are some constraints here. From a practical standpoint, if the distributors are small, then perhaps we want only one distributor in an area. We don't want to have competing distributors. And we don't want to have one distributor serving two or more areas. That would be stretching the sales staff. And, of course, there's a budget limit. And in this example, the limit is $150,000 at the inception of the expansion program. So these are the three constraints that we're going to apply to this particular example. Now, from the viewpoint of forming combinations, we can say that within an area, the choice of a distributor is mutually exclusive. We will only select one for practical reasons. We, of course, can select none of them. Across the areas, we say that the choice is independent because we might select area E or F or G or any combination of those. So the areas are independent. And there are some additional constraints. No distributor can have two areas, and if we have the overall budget limit, then that complicates the situation. All in all, we have 64 combinations because we have three areas. In each area, there are four simple combinations. There are four ways to select projects from area E, 4 from F, and 4 from G. So let's look at some of these combinations and how we might form them. In this table, we're simply listing 8 particular combinations. Now, how you list these and how you construct them is really up to you. It's really a nested loop. That's what we're structuring here. So the first combination is to do nothing in all of the three areas. That's no investment. Is it a feasible alternative? Well, technically, yes, it's feasible. The second one, we're negotiating with distributor V in area E and doing nothing in the other two areas. Again, that's feasible. Out of these 8, 7 of them are feasible. The last one is not feasible because we've got distributor X in both areas E and F. And we said we did not want a distributor serving 2 or more areas. So that's technically infeasible. Here are some more combinations. The first 6 on the right are feasible. The last 2 are infeasible because they exceed the budget limit. The very last one has an investment of $175,000. That exceeds the budget limit of $150,000. And the one before that also exceeds the budget limit. Well, there are 3 more tables like this. We'll just go through them and show them. In this table, the second alternative here is infeasible technically because we've got the same distributor V, serving two areas. We said we didn't want that. And then some of the alternatives on the right are infeasible because of the budget limit. Others are infeasible because of the technical restriction on having two areas served by one distributor. So here's the third table, some more combinations. These are some combinations where we have some very high investments, so anything that exceeds $150,000 is infeasible from the financial viewpoint, and then there are some that are simply technically infeasible because we've got distributors serving two or more areas. And this is the last table. You notice all these four are infeasible because we've got the same distributor serving areas F and G. So there are the 64 combinations. We throw away the ones that are infeasible, either for the technical reason or because of the budget limit, and then we would simply apply the present worth procedure to select the best combination. So that's the procedure for very involved problems where you have both mutually exclusive features and independent features structuring the alternatives. Let's look at a different example. And let's consider three independent options, A, B, and C, with the cash flows that we show in the next table. And we want to apply the rate of return method to select the best option. The minimum attractive rate of return in this example is 15%. So here are the options. We've got A, B, and C, investments of 30, 15, and 20,000. Each project has a lifetime of 5 years. The cash flows are even. That makes this problem particularly simple. It would be an easy table lookup procedure to get the rates of return. Now, looking at the investments, we have to start with the smallest one. That's B. So we'll examine B first. And then if that's acceptable, we'll compare C with B, and so forth. And the last one, of course, will be alternative A. So let's look at alternative B. Here's the expression for the present worth. We want to set that expression equal to 0. This is a series present worth factor. And we isolate that, and we get the present worth factor for 5 periods at 2.43546. Using a table lookup procedure, or maybe a calculator or a spreadsheet, we find that the internal rate of return, or the solving rate, is 30%. And since that exceeds the minimum attractive rate of return, we'll accept B for now. B is an acceptable project. It's the smallest one, so it becomes the defender in this process. Then we look at the difference between C and B. That's an additional investment of $5,000. The additional return, of course, is the difference here between 75.46 and 61.59. This is the present worth equation. We set that equal to 0, and then we solve for the series present worth factor, 3.649. Using a table lookup procedure, that leads to an internal rate of return of 12%. That's less than the minimum attractive rate of return. So we reject alternative C. So B remains the defender, and then the next step would be to compare the next alternative, which is alternative A, against B. So here we need an additional investment of $15,000, additional return, the difference here between 11,000 something and 6,159. We set that present worth equation equal to 0, isolate the series present worth factor, 2.99. That leads to an internal rate of return of 20%. That exceeds the minimum attractive rate of return, so we accept A. So we've run out of alternatives because this is a situation where the basic projects are mutually exclusive. Our final selection in this example is alternative A. Now we'll proceed to the last example. Here we have two independent options, A and B. Cash flows are shown in the next table. And we want to apply the benefit-cost ratio to select the best option. Again, in this example, the minimum attractive rate of return is 15%, and we want to sequence these projects for analysis by size, and A is the smaller project, so we'll look at A first. Here are the cash flows. We've shown the outflows for each time period for A and B, and the inflows. We need this separation to apply the benefit-cost ratio. We'll assume that the inflows are the benefits and the outflows are the costs. So let's apply the ratio to alternative A. the present worth of the benefits, $232,284. Present worth of the costs for A, $152,753. That gives us a benefit cost ratio of 1.52. That's greater than 1, so we accept A for now. Next, we'll consider the difference between B and A. So we have to look at the present worth of the difference in benefits. Present worth of the benefits for B are $252,355. We subtract from that the present worth of the benefits for A. That leaves a difference of $20,071. Present worth of the costs for B are $154,525. Subtract from that the present worth of the costs for A, $1,772. And then we take the ratio of that, 20,071 divided by 1,772. That gives us a ratio of 11.35. And since that's greater than 1, we accept B. That's the last of the alternatives to consider, so B is the final choice in this example. So what have we done in this lecture? We presented a rather elaborate method, a brute force method, for defining combinations of independent and mutually exclusive alternatives. And it's an enumeration procedure. And then in that example, we eliminated alternatives for two reasons. We eliminated them for technical reasons, or you might say marketing reasons. And we also eliminated some for exceeding the budget limit. And then we demonstrated a selection process for some involved situations using rate of return with the incremental method and the benefit cost ratio with the incremental method.